Good morning, I'm Javier Monteagudo. I'm a student of the Politecnical University of Valencia and I'm doing Erasmus here in Odyssey. And I'm today here to talk and present about my project, folding 3D print parts. This is the table of contents. First, I will do a little introduction. Secondly, I will talk about the tools and equipment I have used through the old project. Then I will talk about the improvements and results I have managed to reach. Then the same with the implementations, and finally I will talk about the click system and the future of this project. The main subject of this project is the robot Ragna, for which previous Erasmus students designed the mechanism and made legs, but with earlier versions. My main objectives have been to find a relation between SolidWorks sheet metal model and the final bend result, to improve and study the existing solutions for 3D printing, and to search other solutions to bend the 3D print parts. And then all this applied to the leg of the Ragna robot, that it's print like it's here and then is folded. Throughout the project, I have been using the Mark II printer, that is this one. And with this printer, I have used the materials of onyx and fiberglass to reinforce onyx. Onyx is a fusion through engineering nylon and carbon fiber. It offers high strength and chemical resistance when it prints alone, and it can be reinforced with many types of fibers. And fiberglass is a common type of fiber reinforced plastic that it also offers high strength. To model and design all the parts, test, trials I have made, I used SolidWorks, and to convert all the designs into physical parts, I have been using Eiger, that is the software of Mark IV. Here are the settings I have used in Eiger. I have used the Jairo file, that is that one, with a 28% of field density, 4 roof and 4 layers, and 2 wall layers. And now the fiber, I use a concentric fiber and only on the inner holes. In all the bent pieces must be always one hole or more. So to determine how the size of the hole affects to the strength of the piece, I have made a tensile test with different types of holes. And I also have made the tensile test with pieces without fiberglass to determine how much strength provides the fiberglass to the piece. I have made 5 tests per each type of piece. The size of the holes have been 10 millimeters of large by 4 millimeters of weight, and then 15 by 4, 20 by 4, 25 by 4, and the same with 8 millimeters wide. This is a detail of the piece after the test. Here are several, and there are the graphics. But because it's not so clear, I will show you. These are the graphics for 10 by 4 and 15 by 4. The lower is the 10 by 4. And you will see that when it's the larger holes are more reliable because they have more fiberglass. Here you see the lower curve is 20 by 4 and the other 25 by 4. And the piece without fiberglass is much less reliable than the others that have the middle or less. The bending slot. this was the bending slot that the previous Erasmus students used, with a gap of 0.95 millimeters between the bottom of the bending slot and the bottom of the piece, and in the middle it has 5 glass in the layer number 5, because each layer is 0.1 millimeters, so between 0.4 and 0.5. The problem with this bending slot was that after the bending was a gap remained here, and to solve this problem I made a test and tried different bending slots, and I conclude that the best is this one. That reminds the measurements of the 0.95 and 0.5, but I added 2 little walls of 0.24. With this bending slot, all the advantages we had with the previous one, we remain and we solve the problem. There were a lot of problems, and one was the alignment of the leg after the bending of the 3 holes that have the leg, and due to the axis have to pass through these holes, there was a big problem. And initially all in SolidWorks was good to provide a good alignment, but there are settings in SolidWorks in the sheet metal functionality related to the bending, and one is the K factor. The key factor is the distance between the inside bend to the neutral axis divided by the thickness of the piece. The neutral axis is the line inside the piece that have the same length before and after the bending. The key factor is a value between 0 and 1 as a fraction, and the lower K factor value, the closer the neutral axis is to the inside bend, as you can see in that photo. In SolidWorks, the key factor value was default set to 0.5, but in our case was not correct, because due to our mechanisms of bending, we have the neutral axis in the middle between the bottom of the bending slot and the bottom of the piece. That is, since the top of the piece, 3.55 millimeters. And the neutral axis match exactly with the layer with fiberglass. Therefore, so our K factor is 0.8875, that is 3.55 divided by 4. And with this K factor, the problem with the alignment is solved. Another critical component of the leg was these gears that are in one side of the leg, and in most of the leg did not work correct. So I redesigned them, as you can see, and connect them with a flat axis. And now they transmit the motion and accompany the movement perfectly. These are the gears while printing, and the video shows when I was doing the flat axis. Due to the length of the leg, when you bend it, not all the leg remains perfectly, so we have to use glue while we are bending. The different types of glue that we had in our laboratory were Loctite 406 alone, or the possibility to add it before Loctite SF 770, that is a primer, and Loctite 3090, that is epoxy. To determine which glue is better for our application and which glue have more beneficial properties for our materials, I made another tensile test, and the test pieces of the test allows to glue 90-degree angles, but also allows to clap it on the bottom and on the top. The test consists in 5 pieces per type of glue. Here are the graphics for Loctite 406. This is with the primer, Loctite 406 with primer. And here the epoxy. So we conclude that the epoxy is the best glue. So I have used epoxy in the legs. After all this, I have applied all the improvements and results I have showed to you to the leg, and I have print with all this. And as I said before, this is a printing, and then it's folded. It consists with 8 holes in the middle bend and 2 holes in the side bend, and there are also 2 more holes to allow pass 2 bars to assist with the 90 degrees bend. Another problem was with the slip of the leg, of the bottom of the leg, that was slip and was not suitable. So I have designed rubber rings supports, and now the bottom of the leg is not slip and is much more suitable to be a bottom of a robot leg. And also there are other different completely ideas for bending 3D print parts, and among that are the snap fit joints for 3D printing. In 3D printing, joint refer to design a model that allow interconnect parts without relying in an external adhesive such as glue. And all the 3D snap fit joints share a common element such as hook that is deflected during the joining operation and is attached in a hole. And there are many types of snap fit joints. Here there are 3 examples, but all the types have his advantages and disadvantages, but the most suitable type for application is the click system. The click system. I redesigned a click system for 2 angles, a 90-degree angle and a 135 angle, that are the 2 angles that are in our leg. And the most complicated part in the design was the hook, that is composed by 2 ellipses, and if you change the inclination of the ellipses and the length of his axis, you can change the angle of the hook. But with larger pieces, with bigger pieces, it's much more complicated. So it will be require a lot of study, printing and test, but the future of the project is in that, in study the click system and be possible to make with bigger pieces, and why not with an entire leg. And another future direction of this project is to study other snap fit joints and maybe not create a new leg. And that's it. Now we are try to do a little demo of the robot.
Hello, I'm here to assist with the electronics parts of the mechanical robot because the electronics was not part of his subject. Maybe first I increase the screen. It's very now. Maybe you pick the robot up on your hands and then I will move. Yeah. So now it's unpowered. Yeah. Switching on. Okay. Yeah, can you lift it up? Yeah. Putting it in the middle stance. So this is the stance that the robot is. The servos are in the middle, so it's not perfectly nice looking because it depends on how you connect all the various parts. And this is the normal stance. Yeah. Yeah. Can you clean it up a little, that it looks straight? Yes. Right. So it can support the weight. Yeah. Not that great, but it's a good start. Then high stance, take care because it will be wobbly. Yeah. The reason why this fails is because it's slipping on the inside. One of the belts is apparently not well connected, so yeah, the next guy has to solve this. But if it shouldn't slip, then it will look like this, so it will be good. Normal stance again, and then low stance. Voilà. Voilà, that's it. No, I'm done.
Now, if you have questions or doubts.
Okay, I will start. So, first question is, you chose a technique for flat printing and then bending. Yeah. Is this something that you would do also industrial, or what's the benefit of this technique versus printing in one piece? You could also print the food pack in fact in one piece.
Yes, but the benefits of fold a print piece after this is because of the fiberglass that it's print only in one way. But if you flat the piece, the fiberglass is in the two ways, so have the benefits of the fiberglass in the two ways.
Yeah.
This is the principal advantage.
And it's a dual extrusion printer, or is it, or you had to swap the spools?
No, it's in the printer. Here are the filament of the onyx, and here inside little is the filament of fiberglass, as is in one way. When you can put in the Iker software in which layer you want the fiberglass,
Okay.
and they put fiberglass in this layer.
When you use the bending slot, you also check the orientation of printing when passing the bending slot, like perpendicular to the slot or parallel to the slot. Did you also check that? Because there's going to be a difference if the remaining material underneath the bending slot is perpendicular or parallel to
the bending slot, you mean?
Yeah.
Yes, I checked, but I did a lot of tests with different bending slots, and this is the best. It's all the advantages that have the bending slot of the previous Erasmus student. It remains, and the problem with the cap is solved.
Did you print parallel to the bending slot or perpendicular to the bending slot?
No, if the bending slot is when it's diagonal, it's printing parallel.
Okay.
On your slide 15.
15.
correct that the glue failed before your small piece there failed? You do a tensile test at the right hand side.
Yes.
So you make a very big cut in your ends that you clamp into your tensile machine.
Yes.
Yeah. So it's only 3-4 millimeters, I think. So were you able to test this, or did you have to do something else?
Sorry, I didn't understand.
Well, so you have a very weak point just at the clamps of your tensile machine.
Here.
Yes.
Yes, but because it has fiberglass in the concentric in the holes, the glue broke much before than this.
Yeah. So,
That doesn't affect to the test.
so based on that, if you know that, I was expecting that. So the second question is then, based on that, is there any possibility to make your part in general thinner? Isn't your part over-designed? Can you make the legs thinner, 2 millimeters? I don't know.
Yes, maybe yes, but
Because your weakest point is your glue.
yes, I know, but if the part is thinner, the part bottom the bending slot that is now 0.95 millimeters will be the middle like 0.45 or something like that, and with that measure is, I think, will be problems.
What can be another reason of keeping your thickness for that leg? If you make it thinner, what's the other risk that you would have?
The other risky, I don't know. It will be a lot of riskies, and onyx also is a good material, so
Because here you're testing in one direction, tensile strength, that's correct. But I think if you would make it thinner, that your risk on torsion would be
yes,
much bigger.
maybe yes, yes, you are agree.
What temperatures did you print? Is onyx to be printed? Just out of curiosity.
300 degrees.
Okay, that's fine.
The bottom of the extrude 300 degrees.
And the fiberglass also?
Yes, similar.
Yeah. You are making some connections on with gears and belts, etc. If I
Yes.
understand it correctly.
Yes.
How is your material behaving versus wear and versus slip?
Versus this.
First versus wear. So how wear resistant do you think this would be? Is this designed for life? And
These years.
50 years from now, everybody will say, you remember Javier?
Maybe onyx, yes, because it's better material. This is with onyx, but this is with PLA. That is the other
The standard.
the standard filament. I don't know if you depends on the use that is gonna be, and the yes, depends on that, on the use. If you don't use a lot of time, but Mark Fork entrepreneur say that onyx is a very good material and it have many uses for the industry. So
Now what's the basic of onyx? Is nylon or?
yes, the basic is nylon with carbon fiber.
So any specific things that you need to do with your onyx or?
Yes, with the filament of onyx, to don't open the box until you have the filament end, and to put in no without humidity.
That's important, yeah, indeed. Yeah. If it's nylon, it's sensitive for humidity indeed.
don't speak English, obviously. Nee, maar voor de opwarming moet je dan niet beter geloven.
To bend it, how did you bend the piece? Yeah, so was it just bending or did you do something else?
No, just bending and glue it, bending, and then assist with these bars.
Yeah. So there's no risk that your remaining material is being overstretched and cracking? Is the onyx able to because at the end, if you, I don't know if you have a cross section. I understand what it means. So, if you have a cross section of your cutout there, I think it was on slide 13 or 12 or something. Yeah, there. Yeah. So, is there any risk that when you bend everything, that everything which is at the most down layer, that this, yeah, at the outside, at the down,
Okay.
at where your origin is of your, yeah, if that there you see crack marks?
In some pieces, yes, but if you put the fiberglass well, you didn't see marks. This is perfect. Depends on of the piece and if you bend it little by little, there are not cracks. But if you bend a lot of times, yes.
1 millimeter can look at.
If you are always bend it and unbend it, doing like this, yes, there will be cracks.
Is it? Yeah.
There will be cracks down the fiberglass. Here is very difficult. And here, but if you bend it a lot of times, yes. But if you do it one time and glue it, no.
On your slide 21, I think. I didn't write down the.
This one,
No, one other with the hooks.
this one.
Yeah, this one. Yeah. What's the biggest risk of failing here?
The biggest risk of failing is the hook. That
And
here is
where?
a weak part. Here is a weak part, and the biggest problem is that doesn't fit perfectly the angle. In most of the cases, yes, it hook, but the angle is, if you design an angle of 90, you have an angle of, I don't know, more than 90, 100 or 92. It's difficult that to fit perfectly, and the weakest part of the design is the part of the hook.
But if you, okay, that's one part. And but if you open this 100,000 times, I don't know, yeah, it's for industrial design, a button in a car, whatever. Where do you would expect most failure?
That in this one, because when you are bending it, these are doing like this and then this, so the most critical part is that one.
Okay.
Also, it's a point if you are clicking and unclicking all the time, it would be probably a failure. In the design of now, if it's improved, maybe not.
I have no further questions.
Okay. So thank you.
Thank you, Javier.
Thank you for listening.